Okay, now let's do this new task, which we are asked to write down some formulas for the relative positions, relative velocities, rotations, and relative angular velocities for this configuration. Knowing all of this crap, and also this crap. And this is the third time that I record this video because I made a series of mistakes in the previous ones. So let's look over what those mistakes are. The first mistake, which is very, very common, and from now on we should never repeat, is we assume that, oh, good lord, this is x3 and this is y3 and the origin is here, so this one must be the joint 3. But it's not. It's easy to make that mistake and to think that the coordinate systems always gets attached to the joint, but the DH convention tells us to choose in the axis in a very arbitrary way. So actually this is the first joint, second joint, and third joint, and here's the fourth joint. So even though this axis here is labeled as the axis 3, it actually belongs not to this one, but to this one. Is that clear? The second mistake that I made is that I assumed that these are all 90 degrees. I mean, they look like they are, but the exercise gives you all of these parameters, and they don't make the assumption that these are 90 degrees. So just to demonstrate, we might be tempted to say, since these are 90 degrees, it looks like it, that the coordinate, well actually the y coordinate of 3 inside 2 is this one, right? And this one is what? Well, this one, since these are 90 degrees, I would conclude that these are the D2s. But this distance, and so we would say, well, the y coordinate of frame 3 would look something like negative D2 right here. Something here is the x, something here for the z, and the negative D2 would be over here. Unfortunately, that's not true, because it's only true, and we'll see why just in a minute, it's only true when this angle and this angle are 90 degrees. But the task actually wants us to give them into these kind of parameters. So it's actually not D2 because it still depends on some rotations. And imagining all of that in our head is kind of painful. So for this one, it is recommended to look at the Formulhilfe right here. Oh, sorry. Here. And in the Formulhilfe, in this particular, I think I should download this one. Now, I mean, in this formula right here, as you can see, it's not seeing too well, but this one gives the recursive formulas for the DH parameters, and so they are splitting it in two cases, one for Dregelink and one for Schuppielenk. And this is based on I. So they give every formula for the R's, V's, and also the relative velocities, angular velocities, I mean. So the better thing to do here is actually to copy from here, right? So the first one, we're going to work with 2 to 3 first. And so here our I is 3, and the 3 is here, and it is a Dregelink. It's rotating. And so if you go to that formula, we're going to see it is equal to A2 negative sine alpha 2 d, I think d3, yeah? Yes, it's d3, and cosine alpha 2 d3. Let's write that a little more neatly. A3 negative sine alpha 2 d3 and cosine alpha 2 d3. That would be correct. The second one we want is V 2, 3 to a tooth frame. And the same one we have, since it's I is the Dregelink, we use this one. And we use this particular formula here. This one. And it is simply, it is when you see that omega tilde, just convert everything to a cross product. So it will be omega 2 cross with, cross with the above, R2 to 3. So just copy whatever that thing is above down. Okay, good. The next one is a from 2 to 3. No, actually the other direction, from 3 to 2. And this one's going to be a big one. Well, unfortunately, actually fortunately, we do have the formula for the transform between the I and the V frame right here. This is the parameter, the matrix D, and although the matrix D is actually for a homogeneous transform. We can copy from it the rotational part, right? And so the rotation we can simply copy over. It's very long, of course, it is long. It's cos. Actually, I would just shorten the cos to a c so that we can fit everything. So it's cosine theta I, negative sine theta I. Well, I in our case is actually theta. It's actually theta 3. You can check here, it's given here. Theta 3 is given. It's fine. Zero. Next one is sine theta cos alpha, sin theta I cos alpha v, so that would be sine theta 3 cos alpha 2, cos theta I cos alpha v, so it would be cos theta 2 cos alpha 3 Actually, this is the other way around. Oh my god, this is so messy. So theta is theta 3, yes. Sine is 3, so cos theta 3 alpha 2. Sine theta I sine alpha v. Sine theta 3 cos sine alpha 3 cos theta I sine theta sine alpha v, so it will be cos theta 3 sine alpha 2 So in the third one, negative sine alpha, negative cos, and cos alpha. Okay. And you would also notice from here that theta is always always this index. So theta always goes with that index. We can never see theta 2 here. And alpha always go with that index. So we always see alpha 2 and never alpha 3. Now, is any of that theta, so of course here we see alpha 2 and theta 3, but what are these angles on the drawing? Of course this is not strictly required, but we should know it. Let's check. So it's here, that is the coordinate system 3, and this is coordinate system 2. And also in that formula above, yeah, this one. Let's check. Right. So where is A3? Well, A3 in x direction. That would be this one. So this one would be A3. D3. No, where's D3? In this case, let's find out where alpha 2 is first. So alpha 2 is the rotation between the two z-axes. So this is z2, and we rotate from z2 to z3, and you see it's this rotation. And let's assume that it's 90 degrees, okay? And so 90 degrees, the sine of 90 degrees is 1. So in the 90 degrees case for alpha 2, this one would reduce down to negative d3, which is actually what I thought in my original one. But you see it's rotating, let's see, from 2 to 3, it's rotating like so. And to check if it's negative or positive 90 degrees, we have to look, we have to use the right-hand rule on the x2 axis. And right here we see that it's actually a positive rotation. So alpha 2 is actually 90 degrees. So yeah, this is a review task. Alpha 2, for this one at least. Alpha 2 is 90 degrees. Good. What about theta? Right. Let's see theta 3, because we need it here. Well, in this drawing at least, theta 3 is the rotation angle between the two x-axes. And from x2 to x3, we rotate like so. Yeah? And I say, yeah, theta 3 is actually q3, because it's a rotational axis. But also, in this particular configuration at least, theta 3 right now, right, is actually, well, it's very intriguing, but theta 3 is actually 90 degrees. Right? We rotate from 2 to 3, and it's this rotation, and we check that it's positive 90 degrees because we use the right-hand rule. Actually, it's a negative 90 degrees rotation because y2 is pointing down right here. So yes. So q3. So theta 3 is now 90 degrees, I think. My question is only, is theta 3 equal to q3? And my answer would be yes. Yeah, I'd say so, yeah. So in this current instance, it's actually 90 degrees, and theta 3 has to be equal to q3. But just in case that this is not true, although I'm pretty sure that it's true, I'm gonna ask my supervisor tomorrow. But I'm 99% sure that theta 3 is actually q3. Okay. Now let's try to see. Okay, there's another formula for the relative rotational angle, or the relative rotational velocity. Let's check the formula right here. And for Drehgelenk, this one is true. So it's actually just the elementary vector z multiplied by qi dot. So it's actually, yes, it's actually q3 dot times the az axis, and the az axis is, in this case, this one, or but that sounds strange, right? Because the angular velocity of 3 relative to 2 is rotating around this one. See that? And this one is theta 3 dot, which is also q3 dot. So I don't know, I mean, I would just write it as q3 dot. And the z-axis is here, and this is the z-axis of 3, which, if you actually want to write into the 2's rotational 2's coordinate system, the EZ here has to be replaced with, I think, this third column. So there will be 0 sine alpha 2 and cosine alpha 2. To make the transition more clear, I'm just going to be circling that and putting it here. Now, just as a sanity check, alpha 2 is 90 degrees, so sine of 90 degrees is 0, and cosine of 90 degrees is 1, so it's like 0, 0, 1. Oh, actually it's 0, 1, 0. 0, negative 1, 0, because alpha 2 is 90 degrees. And does that make sense? Well, it makes perfect sense, because this is the vector omega 2, 3, and if we write it in 2's coordinate frame, which is here, then obviously it's pointing up like that, and the y vector is pointing down like that, so the y component is indeed negative 1, and every other component is 0, so that makes perfect sense. So that is a sanity check, and it actually is correct. Okay, so that is the complete derivation for from 2 to 3, from 2 to 1. We'll do that on the side right in a minute, but it's kind of long and it's kind of repeating whatever that is doing. So I'm gonna pause the video now, and I'm gonna solve it, and I'm gonna edit the video so that they yeah.